Okay, so for today, I will continue the sections. We have done the optimization. The section after this is actually with Newton's method, but I will skip that. It's another approximation similar to what we've done the linear approximation, but this is rather than finding the f of x, the Newton's method is we need to find the x itself, the root. But I think I will skip that, and I'm just giving you additional video, just showing you what this Newton's method is, and it's not going to be in your exam, so it's just like a supplement, it's optional for you. And after that, we still have, it's still in chapter 4. We call the antiderivative. It's like a pre-introduction to integral. And if we finish that by today, it's a short section. We are going to introduce to chapter 5, which is the integral, definite integral. Okay. And for reviewing some of the chapter 4, I will leave that for tomorrow. Okay, tomorrow. So if you have a question, any questions on, I think I give you some exercise. You can let me know which part that from those exercises that you need, we might still need some review or maybe some discussion in class. Okay. I think 2 or 3 will have from my exercise. Okay. You can check the exercise on Moodle. Okay. So please let me know which part on that exercise that still need to be reviewed. Okay, so let me give you some questions. Okay, I think I give you some questions here. Wait, oh, not yet. Okay, let me give you the questions that's supposed to be. Okay. Okay. I think if you want to take picture, we can try maybe after the class. But I would like to start maybe 1 or 2 questions from this 4. Maybe 1 question first. Do you have any idea which one we would like to discuss? First, second, third, fourth.
The first one we already.
Oh yeah.
Did it at the TA.
Oh yeah, yeah. Another 3. We have another 3. Which one? 61? 62?
62 is interesting.
62. Yeah, it's short, but the way it's giving you the functions like seems like curve, okay? But it's asking that which one or which point when the tangent line have the largest slope. Okay? So if you don't like really careful on what this statement, you might get confused in how to get this answer, how to get the solution from this the largest slope. Okay, good. Let me start with 62. So we have the curve. So 62. So we have the curve. Okay. Okay, tangent line. So or let me derive this first. Okay, let me derive this first. Y prime becomes 120 x squared minus 15 x to the 4. Okay, let the slope equal to some n. And remember that our y prime in every curve, that this will equal to our m. Okay, and at some x, maybe we can take x equal to a. Okay, then our y prime a, or we call this as ma, is equal to 120a squared minus 15a to the fourth. Okay, now, before we get confused on what we are, how do the process is. First thing, this is our curve. The question is asking the tangent line, what point of the tangent line that it might have the largest slope. But first we need to decide what the question is asking. What is the optimization? Is it this one or this one? Which one we need to optimize? It's asking the largest slope. So the slope itself is our model. Do you get that? So the slope, because the slope is the one that's being asked, the largest slope, that there will be several slopes, right? So it's asking the slope will have the largest possible. So that's the one that we are going to find. So when we put some points A, we want the slope to be as large as possible. Okay? So this being our optimization model. Okay? So let me write here. We want largest possible slope, which means that this is our optimization model. Okay. Now, being said that this is optimization model, what we are going to do next? If we know that this is the model, what we are going to do? Idea? Yes, derive one time. So derive again. So we got m prime. So this m is model. So if you want to optimize the model, we derive and equaling to 0. Okay? We always take the derivative equal to 0. So the first derivative equal to 0. But in our case here, sometimes you get confused and you are going to derive this equal to 0. Right? So this is how we understand the problem. The problem is said that the largest slope from the tangent line of the curve. So we have the tangent line and we have the slope. But the slope itself, we need to find the largest possible. So we are going to derive one more time. Okay, you get it? Okay. So before we going through all the derivative, we need to understand the objective, okay, from the question. And in optimization, it's always start from either finding the constraint or optimization model first, and then you can equal it to 0. Okay? So let me write here. The models that we take is okay. Now optimize the model by taking first derivative. So we take m prime a. This will be 240 and 60a cubed. We can factorize, I think, 60a is 4 minus a squared, right? And we can take that when it is equal to 0. We can write, or we can factorize this first to get the 2 plus a like that. So we can check all the points just to make sure that we are getting our largest possible. So this is a equal 2, a equal -2, a equal 0. So -2 is here, 0 is here, and 2 is here, right? -3, when a is -3, it's minus, so become positive. Let me write here positive. And then -2, 0, well, maybe taking a is -1. -1 is 1, 3, but it's negative, so multiply with negative. So we check to the m prime, okay? And then 0 to 2, we take 1 is positive, all positive, nothing wrong with that. 3, 4 minus 9 is negative, negative, positive is negative. Okay. So it's increasing here. So increasing, we can write from -infinity, -2, and then 0, 2, and decreasing. So -2, 0, and 2, infinity. Okay. So what is the largest slope? We need to take the maximum, right? The local max, at least local max. So we see that this is going up, going down, so perhaps this. And the second one is this, right? It's going up, it's going down. This is the minimum, this is 0. So we have two choices, -2 or 2. Then we can take that point, check, and then the largest one is the one we are going to write as our answer. Okay? So we check. So we find, so finally we can write here, okay, let me write the conclusions. The local max is at x equal -2 and x equal 2. At m2, I think m2 and m-2 is, they will be the same value, right? Because we have even functions, a squared, a4, so it's become both positive. So I think they are having the same value. So that will be, both of them will be our largest slope. So we have 480 and 15 and 16 is what? It's 240, so it's 480 minus 240, right? So it's 240. So the largest slope is 240. So largest slope we can write at the end. Largest slope is when x equal to x equal -2, and slope is 240. Okay, any questions? Any questions regarding this part? Okay. I think other optimizations, if we still have some discussion or maybe some confusing question, I will deal that with perhaps the just additional video by this week, so I will give you several questions. Or tomorrow we can still have discussion on at least chapter 4. Okay, so you might need to review your chapter 4, especially my exercise. Which part from the exercise that you need to discuss more. And if tomorrow maybe not enough time, I will also give you either the answer key or the additional video for some part of the question. Okay, so next week will be our midterm exam. Okay. So is it Wednesday or Thursday? Thursday, right? Afternoon? Because at Wednesday, some of you maybe not really focused. Okay, Thursday. The topics is all chapters, okay, but focus mostly on chapter 3 and 4, mostly. And the topic is until the chapter that I will deliver by today, okay, after this section. Okay, the antiderivative. It's really short. It's really short. Okay, I think I will go through the next page. So this is the last chapter or the last sections in chapter 4. We call the antiderivative. So we are not yet saying the antiderivative is integral yet, okay? But this is how we analyze a functions. When we have a derivative, we would like to know what is the form before we get the derivative. Okay? So let's say a function, we define the antiderivative as a function, the capital F is called antiderivative of a function f, small f, on an interval I if f prime x, the capital, is equal small f, like that, for all x in the interval. So the definitions first is this, okay. But this definition is not complete yet. So we have the following up for this definition. So if the capital F is an antiderivative of f on interval, or maybe let me just write I, then the most general antiderivative of f on interval I is where the c is a constant or an arbitrary constant. So basically, we are going to have, so if we are asking the antiderivative, so the thing is about antiderivative is we are talking on how to revert the form that we got into its original form before we derive. Okay, before we derive. And later we know that we can simply say that it's an integration method. But we are not saying this integral yet, okay? Because the definition of integral is not antiderivative. It's different. It's similar but different. So let's say we have, if you want to find the antiderivative, for example, if we have f of x sine x, so if this is the functions, and we would like to know antiderivative like the capital F x So this is how we see this form. When we derive, it becomes sine. We know that in sine and cosine, they both will have, every time we derive, they will have the form sine, cosine, sine, cosine. And sometimes when we derive, for example, if we have sine, we derive becomes cosine. If we have cosine, we derive becomes negative sine. It has negative. So when we have cosine, we derive become negative. Let me write in here to give you sense of what we have here. So let's say this is cosine x. And if we take derivative of this g, this will be becoming negative sine x. This is the form that we want, right? Here. So when we try to revert this form, it becomes cosine. But cosine has negative, so we need to take negative and then write cosine. Okay. Okay, this process, okay, is also a method later for the, or we call the indefinite integral later. We call this is the advanced guessing method. It's not on your textbook, by the way. So this method is, I believe, one of the best method to solve some advanced integrations. It's really simple, just taking some guessing, but you will get really fast. You will get really fast for taking the integration. Okay. We will do that maybe later, okay, for the integration, okay, for the integrations. Okay, now, so this is the first one. The second one, if we have a function that is 1 over x. Okay, we need to remember what kind of functions, when we derive, we get 1 over x. It's ln, right? Okay? So if we take, for example, another g, that is ln x. This will be equal to 1 over x. But remember, this ln has some unique property that I think we already discussed before, that we might need to take this absolute value of x, right? Because when it's positive or negative, when we derive, it's the same 1 over x. If you remember what we did, I think, in the past few weeks, it's 1 over x. So if we want to take antiderivative of 1 over x, we need to mention this absolute value because we are not sure what is the domain. Okay, so we need to write the absolute value.
And if we have the power, like x with power of, let's say, power of n, n of course is not equal to -1, because we are, n is -1 and it will be 1 over x. Okay, now to take this power, okay, we go maybe taking some examples, like from maybe x cubed, and if we take the derivative, it will be 3x squared, right? So to go from this part into this part, we need to first remove the constant 3, right? And then we need to take this power 2 becomes 3, so we need to add power. So if we think from this derivative form, to make it into our original functions, we need to remove the constant here, so it's defined by 3, and then this is +1. Okay, and we could take this onto another example. For example, maybe x5. And you will see that if you take the x cubed, maybe x to 4, x to 5, x to 6, we see that the same pattern. So we have the constant in the front, and we need to remove that when we want to revert back. And the power, we need to add at least one more power to take it one step backwards, right? One step backwards. So we could see that the forms, if we take, for example, if we take the derivative, like for example, derivative this will the result of derivative, our x power n. So the capital will be x n plus 1 over n plus 1 plus constant. Okay. So you can maybe, to simplify what we've done, to summarize, this is maybe an integral without saying that this is integral, without any integral symbol. We call it anti. I think integral is high school, right? High school, maybe second year, okay, third year. But I would like to know if you haven't taken any integral before. Not yet? Okay. Well, really? Not yet? Not yet? Not yet? Or maybe just slightly introduced? A little? But the method, do you still maybe get the method, like substitutions? Huh? Which part? So you get the integral before? Not yet? Okay. Okay, then I think it would be easier for me to explain. So this antiderivative is like introduction to integral. It's not yet integral. I haven't write any integral words yet. Okay. Okay. For some, I think some special formulas, it's actually similar to with your derivative.
So it's like just revert back to your original derivative. Okay. So let me take this and this. Okay. I'm skipping some of the equations because we don't really need that for now. It's the hyperbolic function here, but I'm cropping those out. So this is actually what we have learned in chapter 3 in the derivative, right? In the differentiation rules. So we have, well, you could read this from the right. You can read from the right. And then you can imagine that the right one here, we derive and we simply get the left part. This is from here, we derive, getting this. So when we have this, like for example, 1 over 1 plus x squared. So every time we have this structure, any constant, and you have another constant here, and you have x squared, or you can simply maybe factorize some structure and you get this. You can write this as tangent inverse x. So you could imagine if we change x into 2x, 3x, or any form for this inside function here, you could still have this as your derivative, right? So you could simply say that, forward and backward. Okay? You could derive and then take the antiderivative. Yeah, this is all the essentials functions and its antiderivative. If you remember the b with power x, if we derive, we have b power x ln b. So when we antiderivative, we need to take that derivative, the ln b out. So we need to cancel. And another important point on the antiderivative is drawing the graph. So if you have a function, just as like with visuals, you should be able to visualize how the functions looks like before it's going to be derived. So it's like reverse to the original function before it goes to by the first derivative. So we are like reversing our process. In chapter 4, I think in the introduction or maybe in the middle, we learned how to draw or how to visualize from a function to its first derivative, second derivative, right? We have like f prime, and then we know increasing, decreasing, the concave, right? But for now, if we take some random functions, we should be able to at least visualize how it looks like before it's going to be derived. Okay, so it's from f prime, maybe we need to look for f. Okay, let's try to analyze and observe. So we say that we have this. Okay. Let's say find the, or maybe sketch the f of x, where f of x is antiderivative of f of x. So we say that f prime x is f of x, right? And some useful information is take the capital F at x equals 0 is 2. So first thing, we can take this
small f as capital F prime x. It's the same thing, right? So we would like to know what kind of capital F in graph. Okay. If we start from this visual, it's actually the same thing what we did before, but it's just reversing the process. If this is the f prime x, so we know the increasing decreasing function already, right? This is all below x is negative, above x is positive, which means that the below will be our decreasing. Okay, this one is increasing. Okay, so from 0 to 2, we are going to have a decreasing function. And we know that from our information here that when x equals 0, the value is 2. So we are starting from here, maybe this one is 2, and we move going down, decreasing. And then we need also to make sure that this is when it's changing. It's negative, it's positive. So from negative to positive, so it's going to have a local minimum, right, at x equals 1. And then this is the slope 0, right, if we derive. If we derive at this point, it's slope 0. So we could say that this is the second derivative equal to 0. Yes, it's a concavity change, right? Yeah, inflection point. So we could try to draw, maybe imagine from here, and then at x equal 1 is they will have some local minimum, so maybe goes there, and then it goes up until 3, so maybe here 3. So it's going to be like this, and then concavity change, and it becomes that. Okay, so this is concave upwards and then downwards, up until the decreasing until, yeah, it's going to infinite point, right? So we say that it's going to decrease, and this is also another slope, right? This is slope that f double prime equal to 0. This is also f double prime to 0. So we have another concavity change. So we are going to have maybe like that. Okay. Because this curve here is not really defined yet, so maybe we just make a rough sketch, maybe just like that. It will be more precise if we have more information, okay? At least for precise points. I think I can give you the graph. And I think that's it, essentials from the anti-drift. It is really short, and it's just summarize your derivative techniques. And the important thing in anti-derivative, we know that we can guess functions that we call the anti-derivative. Before we derive it, we can take it back and refer to its original function. Or in our case here, we could trace the curve back to before it was derived. any questions? Any questions first? After the sections, we need to move to next chapter, chapter 5. Okay. So yeah, we need to make sure we can complete the second part of our courses. So the first part is what you did until this point, that we call the first part of calculus, which focus more on derivative and its definition of derivative and application. And the second part of our calculus is what we call the integral, okay? The integration calculus. Okay? So we start from the definitions, definite integral, indefinite integral, some techniques, and how to apply that to find area, volume, and we should be able to complete until chapter 8, which are the arc length and the surface area. But if not, then I will keep that in our next semester, because I'm not sure whether we can complete up to until chapter 8 or even chapter 7, but we can try first. Right? Okay, we are going to move to next chapter. Okay, so next chapter, so chapter 5. So we begin. This is the integral introduction. Okay, we begin to introduce integral from the problem that we might need to think. For example, if we take this, okay, if we take this, this is a random function. We have x equal a and x equal b. We would like to know how to evaluate this area under the curve f of x. So an integral, it was introduced as a method to get the result of area under the curve. Okay? It was very different from the antiderivative, but at the end they are very similar. Okay? So it's like as the definition is kind of different, but at the end they are very similar. Okay, to help you get through how to take the area, how to compute the area, we could think from our simple functions. Okay? Maybe take the x squared. Okay? Maybe take x squared. Let me give you another picture. Let's take the x squared. How to compute this x? Perhaps if you have learned the integral, the best way to approach this x is we are going to define all this area with a like a rectangle, like a rectangular area. So we could define that. So let's say we define with that, and it has like several pieces. And the next part is we could take this curve and make it into a rectangle. So if we can approach this distance, the small distance here within this rectangle, then the total area is just this distance, the small distance here, multiplied with the y distance here, and then plus all this rectangle, and that's our area, right? That's our area. So we could think from that process. So we could think from here, like that. And we are going to have a break for a while. Okay, so we continue just to observe what we have here, the area under the x squared. Now, for example, in our case here, we are going to have four area, S1, S2, S3, S4, and then we have, since it's 4 area and we have 1 here, so we define by 4. So to make it, the base is 1/4, 1/4, all 1/4. And then we approach the area by using this rectangle. Okay. So first, we are going to compute all the rectangle, the area. Okay. So rectangle 1, rectangle 2, rectangle 3, rectangle 4, sum up all together. So S1 plus S2 plus S3 plus S4. So we have the 1/4 here as the distance of the x, the base. And for the height, since it is x squared, then we are going to take the x, for example, for this part, this is 1/4 and then squared. Okay? So we are going to do that to sum all the rectangle. Let me write R4 as the total area of the rectangle. R is from right. Let me explain later why we call that. So 1/4 multiplied with 1/4 squared. Okay, the first one, and then the second one, 1/4, and then 1/2 squared, and then plus 1/4, 3/4, and then squared, and then plus 1/4, and then 1, and then squared. Okay, let me just compute this, and you can also check if you want. This is 15/32, and this is around 0.46875. Okay. And of course, this is the area for these 4 rectangles. If we see this, all these 4 rectangles, compared with this area that we want to achieve, we want to determine, this area, the total, is less than this, right? Because it has this additional parts. Okay? So we could say the area that we would like to know is less than this 0.46875. Okay? And we could also try another alternative. So instead of taking this, we could take going there. Okay? We could take going to the inside. So we could take the approach for the rectangles. We could take this. Okay, we call this first one here, that additional part, we call this is the overestimate. Because what we have is the result is greater than the one that we want to compute. So it's overestimate, so over our estimations. And when we have this, we call this underestimate. Because we have less area. We have something that is missing here, right? Another way to say, to differentiate the first one and the second one is the endpoints. Okay? The first one, this one, we call also, this is the right endpoints. Why right endpoints? Because every rectangle, they will have an endpoint on the right side. Okay? Okay? The second one is left endpoints. It's on the left. Okay? So this is left endpoints. Okay. Now to combine these two, to see what is in between, we could take this and we could do the same thing. We could take the distance and then multiply with the height. Okay. So we could do the same thing here. So we could take this as L4. L is for the left, so it's left endpoints rectangle. So 1/4. We could start from 0, so let's take 0 squared like that. Although we could skip that, but let me just write that for you. Plus 1/4 and then 1/4 squared. Now we focus on only the left for the height because that is the one that touching the curve, right? And then plus 1/4, 1/2 squared plus 3/4 squared, and then that's it. And this is equal to 7/32, or it's going to be 0.21875. And of course, this is less than the area that we would like to achieve. So we could figure out that the area that we would like to find is between this number and this number.
Sure. Why the next one is 1/2 times?
This one? From here.
Why it is 1/2?
1/4. Oh, this one. Ah, good eye. Why I'm writing 1/2. Ah, okay. Yeah, I also don't know why I'm writing 2. So the area is between 0.21875 okay. But still, this interval is too wide, right? It's too wide. Perhaps the area is 0.3, perhaps it's 0.28, or perhaps 0.4, maybe 4.1, 4.5. It's still less than this. Right? So the area is still too wide. So we need to do something. Okay. And what we can do is, since this is, we define from the beginning, we define with 4. Maybe we could define more. And if you could imagine how we define the functions. If we divide like more rectangles, let me show you here. If we divide here with more rectangles, you see that it will be getting closer and closer to what we are going to achieve. Okay? To what we have done. Okay, let me give you a table for some computations. So when we have the more rectangles, okay, so n is rectangle numbers. So you can see some differences, I think. No need to write all this, but just to see what we have from 10, 20, and then increasing to at least like 1,000. You could get the numbers from the left endpoints, you see, right endpoints. They will come up to one similar number, like 0.33 something, 0.33 something. So this is, I think, good approximation because the error is 0.0001 or 0.001. It's good error. And what's the takeaway from this is the more rectangles you have, the good approximation you will have for finding the area under the curve. And that will left out with the definition for the integral itself. Maybe giving more illustration on how this looks like. If we have this, probably it's too small. Let me just take into the next page. Okay. So the figure is for the upper estimate or overestimate, and this is for lower estimate or underestimate. And you see, if we take the n increasing from if you see from the 10, 30, and 50, you will see that it's getting closer to our actual area. Okay? This is also getting close to our actual area. Okay? Okay, now if you would like to take the first function we have from the introductions, we would like to know the s inside this under the curve of the f of x. What we could do is we could take first is, because it's from a to b, the endpoints, then we could take the delta x as b minus a and divide with how many rectangles we are going to have. If we see the x1, x2, x3 as we've seen in this form, then we could take the x1 is actually a plus delta x, right? x2 is a plus plus 2 delta x. And so on and so forth. Okay. And in general, we would like to have x at some points I is a plus I delta x. And then if we would like to take the right endpoints as we draw here, then it's simply we are going to multiply the base with the height. Okay, the base with the height. So we could take this and write down r n is the number of the rectangles. So we'd like to take the f of x1 multiply with the delta x plus f x2 delta x, and then plus until some n xn delta x. So we could have a definition for the area for this Rn. If we take more and more rectangles as we begin to write before. So we could take the limit, okay, as n going to infinity, as n is going to become large and larger. Okay. So we could take the definition of the area as this. So we could take the limit as n going to be larger and larger, or we can say it's going to be infinite. And the r, we could say that this is going to be all summations, or we could take all with plus all the rectangles area. And this is also same thing with the left. I haven't write that, so let me write the L. The difference is the starting point for the left one is start from x0 and then ended at x n minus 1. Okay, so we have two approaches here, right endpoint and left endpoint. But we want the approach to be more general. So we could take all the conditions, okay, either right endpoints, left endpoints, or at the midpoint. They are all have some restriction. So we could take any points. We could take any points. So we could take as a sample points. Let's say a sample point. So you could take the axis any points between here. Okay, so we could take any points, and we could write this formula into a more general version. Okay, so we could write more general. So you could say that we are going to have not this. Okay, this one. So we could take this as a sample point. So we could take this x1 with some asterisk here. It's called the x1 sample point, x2 sample point. I would take it in every point. Maybe we could just use this to make sure that we could use the formulations in all forms. Okay, not only for right endpoint or left endpoint. We could take it for any point that we want to compute in our curve. Okay, so we could write down that the area is a limit of the x1 sample points until the n. And then we can sum up this f of x delta x, all this f of x, because it's plus plus plus. We could take that as a form of summation, like in the sigma form. So we could write this as
limit. Oh, let's not n. So this is until n, but it starts from I equal 1 of the f x I sample point of delta x.
This is how to write the all is plus f of x delta x. You could write into forms summation and then f of x delta x. And then it starts from I and from I equal 1. And this is the beginning of our introduction to definite integral. So, although when we learn about the anti-derivative, it's not really that similar with if compared with this part. They will end with some conclusion, with the same conclusion. Okay. So, if you are asked the definition of integral, this is the start, the area under the curve. So it's slightly different at the beginning if we think on the anti-derivative, but they will end up with the same conclusion.
Okay, now let's take a look at the official definition of the integral. Okay, this is the definition of the definite integral. It's quite long, but I believe the most important part is the
middle one. Okay? The middle one. So it starts from a function that is defined from a to b in x, and then we divide the ab, the interval ab, into n subinterval is like the rectangle we had before, and we have the width of the delta x, which is the b minus a over n, and then we left all the x will be the endpoint of this subinterval, and then we let the x1 with asterisk be any sample point. So I think that is the previous one we have, right? So the xi, the sample points, they are in between the interval of this xi minus 1, xi, this being the sample point. So in every sample point we have, in every endpoint we have a sample point. Okay? And then the definite integral, the definition is we are going to introduce you these symbols like an S, but it's like long S, like a worm. Okay? And we write A and then bottom and b on top, which means it says that it is the integral from a to b of f of x dx, and dx being the width of the rectangles. And by definition is our limit before. So limit xn going large or going to infinity of the summations from I to 1, this is for the sample points later, to some n of f xi x sample points multiplied with the delta x. So you can imagine this f of x and delta x like a rectangle before. So we have a lot of rectangles, and we simply sum up all these rectangles. And how many rectangles we have? It's so many. We call this is as to infinity. Okay? And of course, we need to provide that this limit should be exist, okay, so that this is can be true. So provide this limit exists and give the same value for all possible choice of sample points. So sample points means that in every point that we choose, they will have the same conclusions and the same results. And if it exists, if the limit exists, we say the function is integrable, so we can integrate the function on this interval a. Okay. So this is, in particular, is official definition of integral, of definite integral. Okay. So if you are asked to integrate some function from some point to another point, with official definition, you need to give you need to integrate using this limit. Okay. Yeah, this is official definition. If you remember, derivative, the official definition is using limit, right? Using limit and then fx plus h minus f of x over h. That's the limit definition of derivative. This is the limit definition of integral. Okay.
We started with root of x. This one is you essentially.
And if you remember the precise definition in derivative, we also have precise definition in the integral, but it's just saying that the precise definition is just like calculate or compute error. Okay, for example,
Of course, this is has limit and this is integral. If we take this, if they have differences, there will be the error. So they subtract this. If they have like small number, that small number will be the error. So that's how your computers works. And they will have like all the machines from what from my perspective, they will have some approximation in their all calculation, like AI or anything, and they will have some error.
okay, they will have some error, like small error that could be ignored. Okay, so that's actually limit, right? Limit is having some small error that could be ignored, right? So we could say the definition for the precise one is minus the sigma this will be less than epsilon. So for every epsilon that is positive, there is integer n, that is n is this is, let me write more clear, n, this is small n, is always greater than this capital N for every choice of the sample point in the interval And also we could call this sum. This is called the Riemann sum. Riemann sum. Okay. And then another takeaway is if we have this, okay.
So the area that we previously described is area under the curve. Okay? But how will we define those area under the curve if we have this kind of up under the x-axis? In the previous examples, we see all the areas here. So whenever we take the area under the x-axis, the area becomes the subtraction of the minus part. So the area under the curve is this plus this minus this area. Yes, it could be. It could be. If you want to evaluate, especially the Riemann sum, maybe we evaluate from these 2 points here. Of course, it will be negative, right? It will be negative. So it could be negative.
Okay, I think I will just stop until here, okay, and we continue about the integral tomorrow a little bit, and then discuss on your exercise. So let me know which part you need to review, and I might also send you the answer key for your exercise. So please at least try 2 or 3 questions from the exercise, okay? So you could have more ideas on what comes in the midterm. I think I already gave you the example of the midterm, like the last one. Well, I could give more example, but I think you could check the exercise first. Okay? You check exercise first. Okay, as usual, we are going to have a feedback questions. Okay, I would like to check the one question about the optimization, another question about the L'Hopital rule. There's 2 questions.
He said to get 0 yet. The most important part is to get the formula.
Okay, I think we could start. Okay, I think all ready. Okay, let's try to start. 3, 2, 1. Not sure the time is okay, but I hope okay.
You could take the ln. You could take the ln and find the ln functions first, take the limit, and then put that answer as the e with power of that ln. Or you could just directly write e with power of ln with that function. Take the limit, and then you need to force out the form to be 0 over 0 or infinite over infinite, right? Yeah.
Tujuh 478.
Okay.
Sini.
So you need to take the ln and you get this form. Right? So this will be L, this will be ln 0 is infinite, so this will be indeterminate products, right? So we need to take this into 0 over 0 or infinite over infinite. Okay? So we need to take this. Perhaps one way to look is becoming like right?
Okay, good. It's 1. 0, you need to e with power 0. Okay, don't forget. Okay, at the end you need to power the e with 0. Who? Thomas Alpha Edison? Who? Okay. Okay, good. Okay, question 2. Get ready. It's around 5 minutes.
I hope it's fast, but I hope it's still okay. It's just exercise. Okay, rectangle. This rectangle, I give you the picture. Okay, and also give you the variable x and y. So you have x. This is x. This is y. And the vertices on the upper side is touching the 4 minus x squared, right? So first you need to figure out the points on this part. So your parabola 4 minus x squared is becoming your constraint. Okay? Remember to optimize the models. So the models is area. So you have x, you have y, you can have the area. And then you can exchange one of them with 4 minus x squared. Right? You can multiply and then derive. And then equal it to 0, you get the critical numbers. Okay? And from that numbers, you can check which one is the largest possible area. At least you get the x cubed something, right? X cubed something, and then derive that equaling to 0. You will see, I think, like square root of 3, right? Something like that. And then just multiply those two, and you will get the area. What's the area? The area is x, y, right? Or you get x. Yeah, and y is equal to 4 minus x. X multiplied with 4 minus x. Yes, okay, fine. So that's the model. We optimize the model by dividing and then find the x, right? Find the x, right? The critical number. Okay. Is it next one or two? Yes. Yeah, it should be to x1. Axis should be to the negative part. This is only one rectangle on the half part.
Oh.
Right? Oh. Yeah. Don't forget the rectangle should be all rectangle, not only the half part. But it's okay, you can just multiply by 2. Okay, if you find the xy only. Okay, so it should be 2x1. Because remember, here you get x, here you get this negative x, right? So you have the distance is to be 2x. So all distance for the rectangle. Total distance. Very easy. I think you get the idea. Right? Yeah, should be 32 over 9. 32 over 9.
Okay. Okay, congratulations. And yeah, your student ID. And if you have any feedbacks, Okay, if you finish, then that's for today. See you tomorrow.